So what this talk is about. So first of all, somebody told me that you're supposed to put up a link to your slides and then speak it out loud. So this is tinyurl.com/dy meetcpp 2023, right? It should open from the phone fine. So now if I see you on your phone, I will assume you're very intensely looking at your slides. All right. So I appreciate you tired, but like, stay with me. Raise your hand if you, at least in part, write C++ for performance. Yeah, so this looks like, substantial percentage of the room, like almost everybody. We give up so much for performance. Like, garbage collector is nice. Like, it's slow, but it's nice. Like, we cannot check array accesses. Like, everybody else is panicking, right? Core dumps, I hate core dumps. But all of those things are there for performance. And SIMD as a technology, I appreciate you don't know, most of you don't know what it is. It's kind of the same way. It gives you very serious performance improvements at the price of your comfort. Like, hiring people is worse than C++, and C++ is already hard, right? All of those things. So raise your hand if you wrote any SIMD. This is much more than I expected. This is very cool. All right, please tell me afterwards, what did you do? But I suspect you didn't do this stuff because it's a bit weird. That's not what usually people do. We're going to do memcmp, copy if, set intersection, and sort. Right? So the thing is that algorithms are very different, and I'm just going to explain algorithms. So this is kind of the closest you can get to a college course on algorithms, except like on SIMD and dance in an hour. So it tends to be pretty difficult. If you can ask me questions and you don't understand, you can shout. I will try to answer, and if we don't make it through everything, who cares, right? It's not a marathon. I know what to cut. OK. Let's do memcmp. So memcmp, right, two arrays. Can you see my cursor? Perfect. Two arrays, we need to compare them, return like, less, equal, greater. Is there a C++ standard algorithm we could use if we wanted to write this ourselves? There are two I know of. Anybody? Stood equal, not quite, because it just returns you a bool. There are two. How would you implement stood equal internally? With which algorithm? Mismatch, yes, that's one. The other one is C++21. It's called lexicographical compare freeway. So now you know. All right. So, but we don't talk about mismatch. And mismatch, at least in code, will do something like this. So you take a byte from each array, and you compare them one after another, right? And then you look at this, and like, can you make this faster? Who can make this faster? OK, yo. So 8 bytes at a time. Right? You can do 8 bytes at a time. Exactly. I'm going to assume that's what you said. All right. So you could do 8 bytes at a time, right? And in theory, comparing 8 bytes should be the same instruction as comparing like one, well, almost the same instruction as comparing 1 byte, except you do 8 times the number of elements, right? OK. There are a couple of like nasty things about it. Like your pointers are not aligned. You have to do unaligned loads. There is like a tail there that is annoying. That is less than 8. By the way, in C++, it's a bit small, but you do unaligned loads with memcpi. OK, you copy from the pointer to the integer and it will do the right thing. All right. Who thinks that if this was beneficial, compiler would do it for you? 5, 6, I don't know, like very few people, you don't trust me very much and don't trust your compiler. You're correct, everybody else. The compiler doesn't do it for you. So this is standard mismatch for chars. This is whatever I wrote within 64s. Does anybody, like, there are 2 reasons why compiler didn't do it. None of them good. And anyone can guess? OK, yo. I didn't quite hear the contract. I don't think so because you don't write. So the answer was aliasing. I don't think so because you don't write anything anywhere. So it shouldn't be a problem. Anybody else? OK. So think about this. Like the way that mismatch would be written, it would be written while we don't reach the end, right? Or while we didn't find the mismatch. So it's not quite equivalent to loading 8 bytes at a time. Because it may be possible that you just said, I have a million elements, but you interrupted the second one, and that's it, right? And you don't actually have the million elements. The mismatch has more guarantees as a standard library function. So they could do it. That's the first reason. And second reason, there is another way to do it. Like, there is this function called strcmp, right? Which has exactly the same properties. Like, you compare strings until a certain size. And that function is vectorized. I'm not going to explain how. You can ask me afterwards. But so the compiler could do it even with these restrictions. Anyways, this is standard memcmp. And standard memcmp, yeah, you practically cannot see it somewhere. It's 32 times faster, more than 32 times faster than our standard mismatch, right? And it's about 4 point something times faster than in64s. And why? It's actually not that smart. There are smart people who wrote this, and I did some really clever things. But for most part, they do the same thing we did within 64s. Only they know that on my machine, you can use 32-byte registers. And that way, you get 32 times speed up. Right? Cool. So what we're going to do today is we're going to learn how to write this kind of code. Right? OK. So, what I didn't mention. So these techniques where you use one instruction to process multiple pieces of data is called single instruction, multiple data. That is SIMD. Right? And these big registers that are specifically designed for it are called SIMD registers. We're going to access them through Eve library. There are many different ways. It's a library. It's on GitHub. It's Boost licensed. It's developed by Joël Falcou, Jean-Thierry Lapreste, and me. However, like, we don't care really about the library today. Right? If you want to learn about the libraries, there's a talk online called SIMD in C++ 20, Eve of a New Era. Right? And we just care about algorithms. Anything that generates you SIMD algorithms should do something like that. And in the library, there is a if algo mismatch, which ideally should do what we wanted here. Let's see how it performs. So this is in 64s. This is standard memcmp. And this is if algo mismatch. Is a little bit slower than memcmp. Like, because they write specifically memcmp, they did more tricks that I didn't do here. However, this is x86. On M1, if mismatch beating standard memcmp substantially on this benchmark. I know why, and I'm super proud of that. I can tell you afterwards, if you want to know. All right. So kind of like seems like if mismatch is the correct thing, right? I mentioned a little bit like on this machine, on that machine. Thing is that when you compile something, you have default target, right? You compile for some like fairly old computer, right? In order to run your binary everywhere. And that old computer doesn't really have all the SIMD extension you would like to use. So in order to take full advantage of SIMD, you need to compile your code correctly. I'm not going to explain how. I'm just going to show you it's important, right? So this is if algo mismatch without just O3. And this is compiled correctly for that machine. And it's a 2x difference. Right. So both of them beat in64 because we know more about the default machine. But still. OK. So let's look inside mismatch. And inside the if mismatch, you'll find diff with the zip, which is very cool. We're really proud of that. Even the ranges libraries, it took insane amount of effort to make this work. But that's not quite helpful as far as the algorithm is concerned. So let's assume that we're going to write this by hand. So OK. Can you somewhat see it? All right. Cool, cool, cool. So what we're writing here is this code that will compare two really big registers, right? So first we accept 2 pointers, right? This is where we're going to take our really big registers from. And first we need a type for our register. In if, this is called if wide, right? And so this on my machine will be 32-byte register. OK. I'm going to load a 32-byte register from both pointers, right? This is us starting to compare those 32 bytes. Then we're going to compare them for equality. So in many SIMD libraries, Eve included, operator equal, not equal are overloaded to return you not just one Boolean, but like a bunch of Booleans. So here we'll return the special type logical, and this is like 32 Boolean values. Does it make sense? Cool. Right. And then we call something called first true, which will compute the position. So okay, let's have a look at the example, right? So 0, 1, 2, 3, 0, 9, 2, 3. Right? The second element with index 1 is true. Right? In this case, first true will return us 1. Right? If there was nothing there, it will return us a null opt. Cool? All right. So most of the time, we will not find anything. Like imagine you mismatch. You go and you compare, they're all equal. You go to the next one, compare, they're all equal. Right? So in this case, there is no match, and we just go to the next register. Otherwise, we need to compute, like, OK, so this was 1, so we will adjust to the place where they mismatched and return that, OK, there was a mismatch. I'll give you a second to look at this, in case you can ask me a question if you want to. Perfect. I will assume not everybody is asleep. Is much as a bit field? Much is optional optional integer, right? So if you have a position, like let's have a look at how first true works. I will show that in a second. Okay? Hopefully, if that question still stands, please do ask it. So I'm going to explain how first true is implemented under the hood, because it's kind of important for understanding how SIMD works. There's a caveat that SVE, there's RMSVE, very fancy new extensions. Those are very different, and their first2 doesn't work like this. Okay. So this is our logical. Logical is usually some special SIMD register, right, representing 32 bools in our case. And we want the first position of the first true, which is this, right? Okay. So on many platforms, there is a special instruction that says any. Are there any truths at all? Right? And if there, and this is our null opt case, right? We can check. Oh, was there a match? No. Go to the next 32 byte. Otherwise, what we do is we construct something in if we call top bits. So this is a SIMD register, and this is an integer, right? Where it's a bit mask, where each integer represents kind of like true or false by bit. Hopefully it makes sense. The only caveat is that to be efficient, it's not always 1 bit, but we pretend on the interface that it is 1 bit. Right? Sometimes there's 2 or 4, but all right. So if this is an integer, and this is an element you want, position of the element you want, how do I get it? Quiz? Anybody? Sorry? Pop count is the number of set, but you are very close. Bit scan forward. In standard C++ standard, it's called count trailing zeros, right? So this is little endian integer. This is like, so this is the first 0, this is the second 0, this is like, so we want to count that. This is standard count trailing zeros. We know at least about this thing. Okay. So, okay. All right. So, yeah. And I'm just going to show you this for the sake of the code. So this is the assembly that function compiled to. Let me make this quick, bigger. I don't know. Right. And so this is top bits construction, like this function. So on x86, there isn't really any that we use. So we just always construct top bits. With this together becomes an any. Well, this together becomes an any, right? And this is bit scan forward we talk about. So this is like the whole first true becomes like 3 instructions. If you didn't understand this, it's fine. It's just showing cool instructions. Okay. There is a standard proposal that you may be heard of standard SIMD. So let's have a look how what we do in Eve compares to what they do. They have different philosophy, but you can, algorithms will map fairly well. So what we call wide, they call standard SIMD. What we call load, they have a method called copy from. What we call logical, they call standard SIMD mask. They have the same not equal operator. And finally, what we call first true, they split into two functions. One is called any of. The other is called reduce min index, right? And it requires that any of is true. So they split out first. I'm perfectly fine with this, except I think that reduce min index is a completely awful name. All right. So if this kind of mismatch happens, memcmp kind of makes sense this point, we're going to go to copy if, unless you want to ask me about memcmp. Like, how it is tails is completely outside of the scope for this. I'm happy to talk about that. All right. So, copy if, right? Like the first time I heard about copy if, it kind of like completely baffled me because copy makes sense. Like you take a big register, you load, you store, right? How do you copy if? There is this notion of compress in SIMD programming, right? It kind of looks like this. So you have a register and you have a mask, and then you take all the selected elements and you kind of push them to the front. Right? So the reason I call this notion of compress and not like a compress function is because sometimes this is horribly inefficient, right, to do exactly this. So instead, in if, we have a bunch of different functions that all have the word compress in the name, and that you use for different scenarios where you would use this instead. The one we want here is something called compress copy. So I have an input array, a mask, and an output array. And now what I do is I take the selected elements and write them together to the output. And then it will return where it stopped. So if you had this function, who thinks they can write a copy if? OK, I have a few hands. Right, well, think about it. You load the register. You test it. OK, you get the predicate. And you do compress copy. OK. There are a bunch of variations to compress copy. One important one is safe, unsafe. So what unsafe says is that it can write a little bit of garbage on the end, right? So basically, it's going to like move elements in your register around, and then it really wants to write the whole register, which means that there is some elements that were not selected written to the end. The second variation is sparse dense. Basically, do you expect a lot of matches or not? Yeah, like sometimes you want like just one element per register or something, one or two on average. All right. Let's talk for a second about the interface of copy if. So this is the interface of standard copy if. First, last output, return an output iterator. Does anybody see a problem for us? I'll highlight it. So the output iterator means that you don't know how much space you have, which means you can never use unsafe compressed copy. You always have to do safe, and this is very slow, right? So in if, everything is ranges based, and then there's like input range, output range, and now I know I can write the whole output range, and I can use unsafe compress. Like there is a little bit of a check because of this for safety now, which obviously we all hate. I'm working really hard to remove the last safety check from there. No worries. All right. There's a bit of a problem, right? So imagine you have 1 million elements, and you copy them into an array of 2 elements, right? Like, OK, you would expect that at some point you fill in the 2 elements, and then you would like to stop, right? So it will stop, but then you want to do something with those 2 elements and continue. So you would like to know where did you stop in the first array. Unfortunately, I couldn't make that work. Like, this is just hard. So for now, just no luck. By the way, I talked to Bryce about this at some point, Bryce Leibach, who led the parallel thinking in the standard committee. Because they have standard and seek now. And I looked at that, and I'm like, how are you doing standard and seek? And the idea there is standard unseek is allowed to allocate. So what it would do is it would allocate you a buffer, copy if there, and then you copy to the output. You know, not amazing, but it will give you some speed ups. All right, let's talk about how compressed copy is implemented. There are two versions in Eve library, fundamentally. One is sort of pure SIMD, where we just throw a bunch of like complicated SIMD instructions in it, and this is way too much to explain here, so I'll just give some main pointers, right? So on some very fancy platforms, you have instructions. So IVX 512, some have, SPE have some. Our main implementation is based on the work of the Stack Overflow user Akrit, with really tiny lookup tables. If you have BMI2 and it's well implemented, Peter Cardes proposed a really good solution that we use. Does anybody know Peter Cardes, by the way, like the name on Stack Overflow? Like he answers, yeah, I see one hand. Peter, two, perfect. Peter Cardes is an amazing person who answers like every x86 question on Stack Overflow. It's insane. All right. And finally, there's a switch and shuffle solution proposed by Zibazon. We use a different switch and shuffle solution, but we still acknowledge his contribution. All right. The second implementation I will explain here, and it's SIMD scalar. This works remarkably well for sparse output when you have like very few matches. We have the input, we have the register, we have the mask. Let's construct our top bits, and let's effectively do first through, right? So count trailing zeros. And then we copy the first selected. OK. Now we clear the last selected bit, do another first through, do another copy. So this is a loop where we go through all the selected elements using count trailing zeros. If you have one or two matches, this is very good. I'll show you in a second. So this is independently was proposed by Peter Cardes and Ilya Arbrecht. All right, benchmarks. So this is standard copy if benchmark. No elements are copied, all of the elements are copied, half the elements are copied. Okay? This is a sparse. So this is the second one that I show you, SIMD scalar, which has bit scans. And you can see that it performs really well when you have very few matches. So in 5%, for example, it will give me here 3.5 times speed up compared to the scalar baseline. Right? Same computer, same machine, 3.5 times speed up of copy if. And this is a BMI2 SIMD solution. You see, it performs very well everywhere, and it gives me like whatever, 3 times speed up here. Question. Looking at this graph of just standard copy if, do you see anything weird? OK. Yeah, you copy more, but give me a sec. If you copy if, what will be the worst case? You copy 0 elements, half the elements, all the elements. Half, right? But here it's not half. Here it is half, right? So this is shorts. Basically what happens is with shorts, I have twice as many elements in the same size, and my processor can no longer remember all the branches. So the branch predictor starts messing it up, right? And when the branch mispredicts happen, the SIMD version gives you more than 10x speed up because it doesn't really have any branches. All right. Is this M1? On M1, the sparse didn't really work, but the SIMD solution gives me what? 4 times speed up. And this is M1 shorts. I just thought it's really cute that it draws an M on M1. All right. So what about the SIMD proposal? Well, they have this function called compress, right? I explained that it's kind of not ideal for some platforms. So they think that they maybe can be able to optimize some of this stuff, but the worst case scenario is basically you will have to know whether or not you can use compress. By the time you get this, the process will be much faster, much better, much newer, so hopefully you will have compress actually shipping. Okay. Actually, how are we doing on time? Let's do sort first. Sort is like cuter than set intersection. Does anybody have a question about copy, if I can answer that? Size of the elements you're copying, what do you mean, like ints versus shorts versus? So that's a very good question. Generally speaking, with SIMD, like the size, the performance depends on the register size. So if you have, let's say, 16 bytes, you can put the 4 integers or 8 shorts. Generally speaking, it means that the speed up for shorts will be twice as big, because you can do 8 shorts at a time and 4 ints at a time. For specifically a copy, if you will end up in a situation of for chars, you cannot do 32 times. You can do only 16 times. Like it was the way I wrote it on my machine. Okay, cool. So let's do sort. Unfortunately, I did not implement sort. Like I haven't gotten there yet. It's a lot of work. But other people did. Here, everything I read on the subject. I'm not going to name everybody, but I'm going to name like specific people I take explicitly from. All right. The key building block to sorting an array is to be able to sort one register. The first time I saw this idea, I came from like a blog called A Question of Sorts by 7 Degrees of Freedom, which I thought was key. And this is kind of how it works. I'm going to explain how you sort 2 elements. And then I'm going to say, and we sort the register. Okay. All right. So this is my register. It's not sorted. And 5 frame. Step 1, I'm going to shuffle the elements around. Like, shuffle is an operation where you take the elements in your register and you move them around. Here, I'm just swapping adjacent elements. So I have 5 free, it became 3 5. Now, I'm going to do min and max. Min and max are both like between 2 registers. Right? You take an element from here, min. Element from here, min. Comes 3 3, 5 5. Make sense? Cool. Oh, sorry. And then I'm going to do something known as a blend, where I take, it's a mixing of 2 registers together. Here I take 1 element from here, 1 element from here. This way I got the register sorted. It's 2 elements register. Okay. And it turns out that shuffle, min, max, and blend are enough to sort any SIMD register. It's just a bit, again, too much to explain here. If you want to know how to do it, there are a couple of keywords you want to look for. So sorting networks, and specifically everybody use bitonic sort. This one I have implementation of, and I still don't understand it. Like, it's very confusing. it is so non-obvious. All right, but works well. Okay. So now, who can say me? There are 3 functions that build up a quick sort. Who can name them? Like, partition, it's the second one in my list, so I'm not going to show it yet. Pivot selection, partition, and the third one? No. Insertion sort. So quick sort doesn't make sense beyond certain size. So when they go to like 16 elements or something, they do insertion sort. Every implementation does something like that. So, okay. This last one, let's see how we can build all of those, right? So this last one is fairly simple. So what if we partition up to a register size, and then we sort the register, right? And then you have like small sorted component of like 8 elements, and then you sort the 8 elements, the whole register sort. Make sense? Cool. Let's talk about pivot selection. Is there a way that somebody sees that you can use sorting of a register to help you with pivot selection? You need 1 pivot, to be clear. Okay, somebody name me a pivot algorithm. Something. First element, fantastic. Doesn't help sort here. Like, but anything else? Well, you need random element, right? But most of them are like medium of 3, medium of 5. Like, so medium 5 is a different one. But like, you select some number of elements, you select the medium between them, right? And you can do selecting the medium with SIMD sort. So let's see how that looks. This code I took from x86 SIMD sort library. Like the top contributor seems to be Raghvir Developali. I'm very sorry if he's not actually the most important contributor here, but he seemed like the most commits at the time I looked. All right. So this is what they do in Intel. So they select elements with equal step, right, through the array. Then they do something called gather, where they load all of those elements together into one SIMD register. And finally, they sort, and this is your medium value. I want to talk about this gather thingy. If it was, I'm sorry. Yeah, I want to talk about gather. The first time I saw gather, I was like, this is the answer to all of my problems. I'm going to write just everything with gather. It seems like super powerful instruction. The problem is it's slow. And there is no magic to it, right? It is either there is an instruction, or they do one by one into array and then load that. There's nothing there. And basically, regardless of how it's implemented, you have to do the loads, right? Well, whatever. You can do 2 loads at the same time on x86, right? So you will have to do those loads. No saving grace. But here, I had never been able to use gather to speed up anything so far. I know some other people have. But here, pivot is kind of not the most computationally expensive, so it's fine. All right. So now partition. Partition is tricky. I take this from, sorry? I take this from, this goes to 11 block by Dan Schechter, I believe. His nickname is Damage Boys. That's easier to Google. All right. This is what they do. So let's take a register from each side of our array and just throw them away somewhere. Like, we're just going to store them on the stack, whatever. We just want some space. We don't care about the values. Now, we're going to take a register. We're going to load it, and we're going to sort it. Okay. And then, using first through, we can find the first position where the pivot would fit. Right? You compare everything about the pivot, you find first through. So this way, we just partitioned a register, right? Everything here is less than pivot, everything here is greater than pivot. Now, to be clear, this is not an amazing way to partition a register. On many platforms, you can do some compress-like tricks to do partition, but for the general purpose of something really weak, that can be not bad. All right. Now, what we do is we take this partitioned register, and this is our space. Like, so this is 2 registers worth of space, this 1 register worth of space. Let's write it into both sides. And then we're just going to say everything before this is sorted, partitioned. Everything after here is partitioned as well. And this is whatever. This is free space. This is free space. Right. So we can try to continue our algorithm by selecting a register here. Because what will happen? We have enough space for a register here. We will have enough space for a register here. All right. Have a think for a sec, because I know this is probably the most difficult one. Like, you have a space, you sort the register, you put it on 2 sides, boom, you have some partition. You will have enough space if you load the register from one of the sides. Okay, if you kind of didn't understand at this point, it's fine. Yeah, I don't have the benchmarks, I don't have this implemented, but just some numbers say 10x, some numbers say 17x, I don't know. Like, the measuring sort is notoriously hard, but clearly there is something there. I think the Intel SIMD sort is now a NumPy. All right. So how are we doing? 30? 20. We can do like most of set intersection. Tell me when it's 5 so we can take the questions or whatever. All right. We may not do the numbers, but we can do the algorithm. It's fine. All right. So, turns out during my practice runs that not everybody is very intimately familiar with all the standard algorithms, and they cannot tell me out of the box what that intersection is. So I'll have to explain. So set intersection is one of the merge algorithms. Like take two arrays and do merge like thingy. Specifically, it looks for equal elements. So you take element from here, equal element from here, compare them, and the smallest one advance. When you find the equal element, you write that to the output. All right. If you have, there can be duplicates. Like it's just arrays, sorted arrays, but duplicates are allowed. The standard defines very well what happens with duplicates. We will not. We'll just relax that requirement. So, and then you go further and finally get the second one. All right. So there are two implementations of set intersection. One is SIMD scalar. Looks something like this. So you have the first array, and ideally it should be a smaller array than the second one, and you have a second array. Now, what we will do is we'll take one element from the first array, and we'll take a register from the second array. Right? And then what I will do is I will take this element and write it into every element of this register. This is sometimes known as broadcast, because I wrote one value into everything. Right? And then we compare this register against this register. So think about it. Like in the scalar version, you compare element against element. Right? Here, we kind of being optimistic. We will compare one element. What if we compare it against first, second, third, boom, right, all of them. And then maybe, if all of them are less, we can just advance, right, by the register size. And if not all of them, well, let's test for equality. And then we will test one against many for equality, right? If equality is true, we have to copy to the output. Boom, we found the intersection. And we advance the first element, array. Okay, I see some nodding. I really appreciate you nodding. This is really nice. All right. The second one is harder. It's from this paper, Faster Than Native Alternative for x86 VP2 Intersect Instructions by Guillermo Diaz-Canas. Kind of looks like this. We have two arrays, and this time we kind of don't care if they're the same size or not, that's fine. What we do is we take a register from each of the arrays, and then we do really expensive operation called has equal in, which compares each element from the first register for equality against each element of the second register. And then what we do is we do compress copy. So what that did us is basically we intersected the two registers. Now we need to advance. How can we advance? Well, okay, let's look at this element, like the last element in the first register. And let's try to find it in the in the second register, right? So any matches for things after it cannot be here. That's for sure. So we can advance F2 here. Right? Because anything here cannot be matched to anything here. Right? Same thing we do in reverse. So if we take this element, look in the other. Okay, that's not the question. Yeah, it's a bit tricky. The thing about this, what is really nice, is that even if you have very intersected arrays, you guaranteed to advance quite a bit. If you don't have duplicates, you can try to prove that you advance by a lot. But okay. Let's talk about has equal in. So it's actually like there was the alternative to VP2 intersect instructions. There's an instruction to do it on x86, but I don't have it, and in the papers they don't suggest to do it. They suggest to do a very silly thing. So you have first register, and you have a second register. Okay, let's compare them against this, and then let's rotate this register. So that way I can compare against, against the first element, against the second element, and against all four elements, like each one. Right? This seems like a lot, right? Like just whatever instructions. But think about it. So this is not always a rotate to be optimal, but there's always one instruction. Right? Almost. Like, as good as it gets. Right. So this is equality, and this is, or like ideally this is port 5, this is like, whatever, part 0, port 1. So in theory, if everything works out, you can do 3 of those in one cycle. Which means that you should do like the number of cycles you have in the register elements, which is pretty good. In fact, in the paper, because they target like really fancy instructions, they merge these two into one instruction by being really clever. Okay. So how are we doing? 10 minutes? Let's do benchmarks. 20. It was 20 minutes ago. All right. All right. So this is a set intersection benchmark, like just standard one. On the left, it intersects small array with a big array, right? So this is 5% of all elements, 95% of the elements. Here is half and half. The number of elements stays constant. The difference is branch prediction. Right. Now, this is let's do this one. So this is a SIMD version, right? So SIMD version is about 1.5 times better on the left, and whatever, 4 point something times faster on the right. And the SIMD scalar version, which was really simple, is actually ridiculously good. This is 20 times speed up on the left. Right? Well, almost 20, like whatever, like crazy. And this is, again, even in the situation where I would not expect a good speed up, where it's the same size, it still gives me like 4.5, which is also very nice. Okay, this is M1. On M1, the SIMD approach didn't work, but the SIMD scalar approach still gives us a really good speed up. This is 10x, right? This is 2.5. All right. In defense of the people who wrote the paper, right? So I'm targeting on M1. We have a 16-byte SIMD register. On x86, this x86, I have a 32-byte SIMD register. You can see that here it performs relatively better. I suspect that this is a dependency, that the bigger register size you have, the better the SIMD approach would perform. They target 64-byte registers, so they should maybe have another layer of speed up over this. Okay. All right. Do you have questions about a sort, set intersection? Or sort? It's also cool. No? All right. So I really appreciate people who work with me. So Joël Falco and Jean-Thierry Lapreste, like they work with me on the Eve library. And all the amazing people who share their research online and I can look at it. And finally, you can find the library on GitHub. You can find the slides, again, tinyurl.com/dy-meet-cpp2023. I did a similar talk with different algorithms called My First SIMD. I cover strlen, find, reduce, inclusive scan, and remove. There's a talk about the library, SIMD in C++20, Eve of a New Era. And finally, on Slack, on CPP-Lang Slack. Who is on CPP-Lang Slack? I see one person. You should be on CPP-Lang Slack. It's just type CPP-Lang Slack into Google and it will find you. Like, it's a really cool place. They have a SIMD channel, which is very low volume with very smart people who will answer things. And low volume until I'm renting. But, yeah. So that's it for me. If you have any questions, I'm happy to answer.
One question to more system architecture rather than now the software side. If I would use SIMD operations on a hyper-threaded hardware, would this become a shared resource then? Because I probably only have one SIMD per core or per CPU. So my hypothesis would be disabling hyper-threading would remove like the shared resource of the SIMD.
So I can try to answer that to the best of my understanding of this. Caveats applied that not the really hardware expert. All right. So with hyperthread, so your CPU core can do 4 instructions per cycle, right? If you have really fancy, maybe more. Like I just always count as 4. So if you can do 4 instructions, you can do like 2 additions, right? 2 SIMD additions, or whatever, 1 shuffle, right? How much do hyperthreads fight for those resources? I would not expect that to be any different from scalar code, right? People definitely use hyperthreading or not use hyperthreading, but it all depends on whether or not they can get up to 3-point-something instructions per core. In something like a compression, yes, you can, like smart people wrote really good compressions or encodings, right? They will get to up to 4 and their hyperthreading will be a disaster. Something which is memory-bound hyperthreading is a lifesaver. Like, so I would not expect any SIMD-specific issues here.
Okay, thank you.
How did the cache sizes on your machines compare to your testing data set for your benchmarks?
Everything fits into that for cache.
Okay. Did you do any benchmarks with memory-bound data?
For this, no. Like, so it is true. The thing is that the SIMD code has this problem, which is basically, it's not really a problem, but you do whatever. With regular code, you do 8 bytes at a time. Here you do 32 bytes at a time, right? You exhaust your cache much faster. There's a paper by Alexander Stepanov where what they do is they do some really fancy compression. I didn't read the paper, I just read the abstract. But they do real fancy compression to kind of trade off compute for just speed of loading data from memory. Right? But just, it's not that like, you couldn't predict as a cache miss, it just couldn't load data fast enough. Yeah. So it is true that sometimes you will be memory bound and SIMD will not help here. Like, I don't know. But as far as benchmarking goes, it's also, I'm trying to benchmark an algorithm and everything else is kind of additive to that. So yeah, I don't think that would give me much. Okay.
Regarding multi-core and SIMD instructions, do you have any experience with the frequency scaling implications of SIMD instructions?
It's a question about frequency scaling. that's somehow like the remarkable thing that everybody heard of. Okay, let me tell about frequency scaling if we have time. So your CPU have something known as power. I learned this last week. I'm repeating what I heard. Your CPU has something known as power license, right? On x86. On AMD, you have just, I don't know if they have power license. They don't have this issue. Right. And I don't know anything about that. So you have a power license. Power license goes like normal integer operations, as float operations, and that includes AVX 32-byte integer operations, and then you go 32-byte float operations, 32-byte float operations, and 64-byte integer operations, and then you go into 64-byte float operations. Whatever, it doesn't matter. Point is that by default, you run at normal floats, so 16-byte floats, 32-byte ints. Right. Everything here is 32-byte ints. We would not have experienced any issues unless you're a high-frequency trader and you do something very clever that I don't know of. Like, so all of your standard SIMD functions, like standard libc functions will be. So if you call strlen, it will be 32-byte ints. Like, just, well. Right, so when you switch, what happens? So your CPU cannot just run those instructions. It has to switch the power license. And there's a protocol. So it has to request a new power license. While it requests, it runs at really low frequency, gets the restrictions, pops up to the new frequency, right? Runs for a bit there. Then it will, then, after a while, you don't execute those fancy instructions. You'll be like, OK, maybe I can switch back. So it drops again, requests a power license, and comes back up. Right. That was at least the story for a while. I don't know, maybe they say that the new Intels are better at this than they used to be. All right, so basically what happens, you use one instruction that just kind of didn't matter, and then all of a sudden, your CPU frequency drops. Right. That's one of the big problems with 64-byte instructions, on top of other things. So generally speaking, as a rule of thumb, you want to use 64 bytes on x86 only for really big computations. Right. Like again, caveat here, I never worked at Intel. I don't necessarily know everything.
You mentioned something about making sure to compile the code correctly.
Yeah.
Would you be able to elaborate a bit on that?
Well, the 64-bit one would be the one. So there is in Eve, it's a complete mess. I'll fix that. But generally speaking, there is a flag that you pass to both GCC and Clang. I don't remember, but you can control the SIMD widths so that it doesn't go to 64-bit. Because by default, something like transform, right, or transform reduce will be auto-vectorized. And sometimes I see those vectorized with 64-bit instructions. So maybe compile introduces that problem for you as a flag. You want to compile with a specific architecture in mind, so just March. It's very good for somebody like me who has a server, right? And I just compile for that servers, or like whatever. I have 3 different servers, and it was also compiled. It's bad for people who have to ship code to people, right? Like I talked to, I don't remember his name. It's a game dev person. Okay. And he says that that people really complain when they have like really old processors with some really fancy GPUs, and they really expect the game to run very well. So what they do instead there is they do dynamic dispatch. They try to determine at runtime which instruction you have or which instruction you have, and then they select. With something like Eve, this is fairly hard to do. So our suggested solution, and that solution that's popular in this industry, is you do DLLs. So you take your kernels or whatever, expensive things, you put them into some special thing, you compile that as DLLs, and then at runtime you load the correct one. In Eve libraries, there is an example of how to do that with CMake. That's my kind of general answer. But just March. Cool. Thank you.